Hello everybody, we start our 14th lecture, so section 14.1, one-sided limits. And I'll start with definition of one-sided neighborhoods. Definition: B minus of A delta is A minus delta A, B plus A delta, A plus delta are left-sided and right-sided neighborhoods. Of A, and of course here we should suppose delta greater than 0. And now we can define A is called, how it is left-sided, just right, left limit point of D if for any delta greater than 0, B minus of A delta intersected with D is not empty. And analogously, A is called a right limit point of D if for any delta greater than 0, right-sided neighborhood intersects our set D. Now we can define left and right limits of a function. So L is left limit, or limit from the left. We show the left hand limit at P of a function f, and it is written as x tends to A minus 0, P minus 0, f of x equals to L if P is a left limit point of D, f is defined on the set D, and for any epsilon greater than 0, there exists delta greater than 0, such that for all x in D which are between p minus delta and p, we have f of x equality f of x minus L less than epsilon. That is Cauchy definition of the left-hand limit at p, and analogously we can give the definition L is a right-hand limit at p of a function f, and it is written as limit x tends to p plus 0 f of x equals to L if p is a right limit point of D, the function f is defined on D, and for any epsilon greater than 0 there exists delta greater than 0, such that for all x in D which satisfy the inequality p less x less p plus delta, we have f of x minus L less than epsilon. These are definitions of the left and right hand side limits. Okay, then example 1. Example 1. F is defined on the set R minus 0, and this is f of x equals to modulo x over x, and let us, in fact, for p equals to 0, sometimes we can write, in fact, sometimes even for p you can forget about this 0, doesn't matter. Also there are notations like f of p minus 0 equals to L, and here f of p plus 0 equals to L. That is equivalent for the left and the right hand limit at a point P. So here we are interested in limit x tends to 0 plus. Of course we can write 0 plus 0, but it's sufficient to write just 0 plus. F of x. Look, for arbitrary delta greater than 0 and for arbitrary x in the right-sided neighborhood, b plus 0 delta, what we have? F of x equals to, if x is greater than 0, then modulo x coincides with x, and that is 1, right? So it means that when we are interested in the right hand limit, it's the same as to find the limit of identically 1, and that is certainly is 1. So in fact, here in the definition, we don't care about delta. So it means we can choose here arbitrary delta is positive, and then this is always 0, identically 0. Analogously, for the left hand limit, we have limit if x is negative, then modulo x equals to minus x, we have minus 1, and the limit is minus 1. Okay, no questions. Okay. And analogously, we can consider the function signum x, signum. Sometimes it is denoted by shorter, by signum x, and that is 1 x is greater than 0, 0 x equals to 0, minus 1 x less than 0. And definitely this function coincides with f of x for all x not equals to 0, right? And since values at 0 are not important for calculations of limits at 0, same equalities, I mean limit x tends to 0 plus signum x equals to 1, and limit x tends to 0 minus signum x is minus 1. Okay. Next example. Example 2. Consider f from R to R, which is defined by f of x plus 4 for x smaller than 1, minus 1, and x squared minus 1 for x greater or equal minus 1. So we are interested in right hand limits and left hand limits at minus 1. Okay, doesn't matter. F of x. Here for all positive values of, and not positive, for all x in the neighborhood, in the right neighborhood, for arbitrary delta greater than 0, and for arbitrary x in the right sided neighborhood of minus 1, we have f of x equals to x squared minus 1. If x is greater than minus 1, then we have x squared minus 1. So it means I can write here x tends to minus 1 plus 0, x squared minus 1, and then we substitute minus 1, we have 0. Now analogously, limit as x tends to minus 1 minus 0, f of x, that is limit as x tends to minus 1 minus 0, x plus 4 minus 3. That is how to compute such kind of. Yeah. Now we can just compare with Cauchy definition of the limit, and we can formulate if P is a limit point of D, f is defined from D to R, then f has a finite limit at P if and only if there exist finite left and right limits, left hand and right hand, left hand and right hand limits at P of f, and they are equal. So limit at x tends to P f of x equals to L if and only if limit x tends to P plus 0 f of x equals to limit x tends to P minus 0 f of x equals to L. That is the same. So why that is true? Because for the definition of the limit, you should replace inequalities here by the inequality x minus P less than delta. And that inequality is equivalent to the pair of both inequalities. So this is satisfied if and only if one of those inequalities is satisfied. And that is the proof. Okay. One more example. Just continuation of example 1. So example 1 implies that the limit as x tends to 0 signum x doesn't exist. Okay, now monotonicity. Definition. And I'll give it for an interval, right? Yeah. Let f be a function from an interval. Finite or infinite doesn't matter, so f is increasing if for all x1 less x1, x2, a less than x1 less than x2 less than b, we have f of x1 less or equal f of x2. And analogously, f is decreasing x1, x2, which satisfy that inequality, we have an opposite. Not opposite, not precisely, yeah? Yeah, that is definition of monotonicity, right? If f is increasing, or if f is decreasing, maybe, then f is monotone on A, B. That is a definition of monotone functions. What does x tends to p plus? Yeah, the question is about what is p plus 0. So instead of p plus 0, you can write just p plus. That's equivalent. Just notation, nothing else. So sometimes people use this notation, but of course you should remember that it's just a notation for this limit, nothing else. You can use p plus not or to write just p plus. Doesn't matter, it's equivalent. Okay, and yeah, strict monotonicity. Monotonicity is for strict inequalities. So if all those inequalities are strict, then limit square root of t. Ah, yeah, good question. Very good question. Let me answer this question. So the question is it true? Is it true? Yes, it's true according to our definition, because square root of x is a function from 0 infinity to r. And 0 is a limit point of 0 infinity. So according to our definition, that is true. That is true. But be careful, because quite often, in many textbooks, a slightly different definition is used, and that is alternate definition of limit. So quite often, when you write something like that, then it means that f is defined in a neighborhood, of course without b a delta, without a, in a punctured neighborhood, right? So from the beginning of the definition, if you suppose that the function is defined in the neighborhood, then of course this is not true. So if you use this definition when you force, so before to talk about the limit, you can ask for the function to be defined in a punctured neighborhood. If you use this definition, then this is not true. But if you use the definition from our textbook, like so the only thing which you ask for is that the point where you want to find the limit is a limit point, But of course, in any case, that is true for any definition, because if we are talking about one-sided limit, then of course the function should be defined in a one-sided neighborhood. That is so. To avoid this difference between definitions, I would recommend to write it like that. In that case, for sure, for both definitions, it's true. Otherwise, you should be careful and so you should understand what of the definitions you use at the moment, right? Okay. Did I answer? I don't know. Okay, let's go further. Next theorem, it's about some properties and very important theorem, theorem 2. So it says that one-sided limits of a monotone function exist. So if f is increasing on AB, P is a point of the interval, then the limits from the right hand side and from the left hand side, okay, I will not use 0 because in our lecture notes it is not used, f of x, and limit as x tends to p minus f of x exists. Proof. Consider the set of the values of f of x where x is between p and b. That is a real set, and for all x from the interval pb, we have an equality f of x greater or equal than f of p, because the function f is increasing. The function f is increasing. So it means that this set is non-empty and bounded below, because it is bounded below by the value of the function at the point P. Non-empty since we have values of the function. The function is defined on the interval. Hence, there exists infimum of this set. So it exists. And I want to prove that indeed that is the right side limit, right hand limit. So we want to prove that the limit, okay, let me denote it by which letter is used. L. No, it was 4. Okay, it doesn't matter. Let it be M. Equals to M, right? In your textbook, the limit from the left is discussed, but it doesn't matter. Okay, so let's prove that is true. What we want to prove? By the definition, we have to prove the following. There exists delta greater than 0, such that for all x in AB p less x less than p plus delta, we have f of x minus m less than epsilon. That is what we want to prove, right? So that is what we want to prove. Okay, so by definition of infimum, what means M is infimum of a set? It means that for arbitrary epsilon greater than 0, M plus epsilon is not least bound for not least. It's not a bound below. It's not a bound below, right? It's not a bound below for our set. So the number is not a bound below. And it means there exists, hence, there exists x, p minus x less than b, such that f of x less than m plus epsilon. then denote by, okay, delta, put delta equals to x, okay, let me write here x naught, let's say, x naught, right? Then x naught minus p. That is a positive number, right? Then for all x from the interval a, b, which satisfy this inequality, what we have. So p plus delta is what? That is precisely x naught. So because of increasing, because of monotonicity of the function f, we have f of x less or equal f of p plus delta, which is f of x naught, and that is less than m plus epsilon. But since x is greater than p, then f of x is an element of this set. Hence, m is a lower bound below for this set. Hence, this is greater or equal than m. Now look at this inequality. So f of x greater or equal than m and less than m plus epsilon. So it means that it follows f of x minus m is less than epsilon, because m is greater than m minus epsilon. And that is precisely what we want. So for arbitrary epsilon, we found delta positive, such that for all x which satisfy that inequality, we have the inequality f of x minus m less than epsilon. So we have proved. And analogously, we can prove, so analogously, we can prove which definition, which assertions. F is increasing, then on AB, P is in AB, then the limit x tends to P minus f of x exists. Also, f is decreasing on AB, P and B, then limits at x tends to P minus f of x and limit as x tends to P plus f of x exist. So that is proved quite analogously. Okay. Now we should write the definition of infinite limit according to lecture notes, but we did it during previous lecture. So yeah, we can yeah. Okay, let's have a break. Okay, let's continue. And now it's natural to consider the case of the ends of the interval. So what is about limit as x tends to b minus of f of x? So we don't make any extra supposition on the function, the same, nothing else. And look, what can we say about this limit? Of course, recall that we didn't suppose, so b might be infinity, right? And if b is infinity, then it makes no sense to write like that. So that was not defined simply, right? We are talking only about limit as x tends to infinity f of x. But about this also it's natural to talk about. So this limit is equal to the supremum. We can prove it quite analogously. For the increasing function, for arbitrary increasing function, that is supremum. But it might be infinity, right? So, because you see, here, for example, we used that it is bounded below because of this inequality. P was in the interval. Now we have no bounded above. So this set is not bounded above. Of course, it is not very good to consider the case when the supremum is infinite, but we accept this. So in this case, we can talk not only about the existence of the limit at a point of an interval, but even about the limit at the ends. Okay, so let's talk about example of an infinite limit. So, example, third example for today. Limit as x tends to 1 over x minus 1 squared equals to infinity. So, what we have to prove? We have to prove that for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x 0 less x minus 1 less than delta, we have an equality 1 over x minus 1 squared greater than 1 over epsilon. In your textbooks, instead of 1 over epsilon is used capital M, but it doesn't matter. So look here, this inequality, last inequality, we have to check it, is equivalent to x minus 1 squared is less than epsilon, because it is positive number, right? X is not equal to 1. So it means that we can take as delta just square root of epsilon, right? That is positive number. And now, so for arbitrary epsilon, we choose this value of delta. Then for all x which satisfy that inequality, x minus 1 less than square root of epsilon greater than 0, then we have x minus 1 squared, it's positive, less than epsilon, or it follows 1 over x minus 1 squared is greater than 1 over epsilon. That's what we wanted to prove. And yeah, maybe one more example. Example 4, just to use similar. It's similar to limits of sequences. X tends to infinity, x power 4 minus 3x cubed plus x over 3x power 4 plus x squared minus 1. So how to compute that example? We write limit x tends to infinity 1 minus 3 over x plus 1 over x power 4 over 3 plus 1 over x squared minus 1 over x power 4. We divide both numerator and denominator by the same number x power 4. And then we use that the limit as x tends to infinity 1 over x is 0. Because just by definition what it means, for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x greater than 1 over delta, we have modulo 1 over x less than epsilon. And look, that is 1 over x for positive x less than epsilon. If x is positive, we can rewrite it as x greater than 1 over epsilon. Hence, we can choose delta equals to epsilon. So, just the choice of delta equals to epsilon guarantees this equality, and then we use arithmetic properties of limits. So tends to 0, tends to 0, tends to 0, tends to 0, and altogether 1/3 is obtained. Okay, now section 14.2, continuity at a point. Continuity. 14.2 continuity at a point. So, definition. Let f be defined on a set R, P belongs to D. Then f is continuous at P if for any epsilon greater than 0 there exists delta greater than 0 such that for all x in D which satisfy the inequality x minus p less than delta, we have the inequality f of x minus f of p less than epsilon. That is Cauchy definition of continuity, and analogously, that is Cauchy definition. Analogously, Heine definition. Again, let f from D to R be in G. Or maybe that is a theorem. F is continuous at P if for any sequence xn and from 1 to infinity in D, limit xn equals to P for arbitrary sequence of this kind, we have the limit of various f of xn equals to f of P. Okay, so proof. Proof is quite analogous to the proof of equivalency, that is Heine definition. And in fact, we can refer, but to refer to the theorem about the equivalence between Cauchy and Heine definitions of the limit, to refer to that theorem, we need to be careful, in fact. Why? Because look, there are two cases. So that is an assertion. Let me write it as assertion. F from D to R, P in D. F is continuous at P if and only if for either P is a limit point of D and limit as x tends to P f of x equals to f of p, or p is not a limit point of D. Nothing else. So if p is not a limit point of D, then arbitrary function which is defined at p is continuous at p. So nothing else. So there are two possible cases. P is a limit point, then there exists such a limit, right? So it means, why now both definitions are equivalent? There are two cases. So if P is a limit point, then continuity is equivalent to the existence of such a limit. And then the theorem follows from the theorem about the equivalence between two definitions of the limit. Or if P is not a limit point, then f is continuous for sure, right? And in fact, this is also true. Why? Because now there is only one sequence xn which tends to P, namely the sequence which consists of the point P only. So P, 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 and so on, nothing else. And of course, the limit of such sequence is f of P, if xn equals to P for arbitrary n. So that is how we can prove that theorem. So once again, continuity, two possibilities. Either P is a limit point, then the limit equals to f of P, or P is not a limit point, nothing else. If P is not a limit point, no conditions, just f should be defined at P, nothing else. Okay? So of course we can rewrite many practically arbitrary theorem about limit can be rewritten as an assertion about continuous functions. For example, so theorem 2, okay, this was theorem 1, right? Theorem 2, if f of x less or equal to g of x for all x in B of P delta intersected with D, P is in D, f g from D to R, then makes no sense. Now we can write like that without P, right? Without P, otherwise no sense in that theorem. Then f of P less or equal g of P. Why? Because of no, that is not true, by the way. P is in D, and P is a limit point of D. Right? So that is just a reformulation of the related result for limits. By the way, let me point out this condition, very important, because if you forget about this, right, then this is not true, because it might happen that this intersection is empty. And of course, for the empty set, everything is satisfied, right? And so if P is not a limit point, then arbitrary functions f and g are continuous, hence no inequality is satisfied, of course, right? Okay. Opposite assertion can be reformulated as follows. If f of p less than g of p, p in D and P is a limit point of D, if G from D to R, then there exists delta greater than 0 such that for all x in the neighborhood intersected with D, we have f of x less g of x. By the way, here I need not to suppose this. That's not necessary here. Yeah, the assertion is valid without this supposition, because if P is a limit point, then it follows from the related result for the inequalities, and if P is not a limit point, then this inequality is satisfied because this intersection contains only one point P for certain delta greater than 0. Example 3. Oops, example 3, I forget which was example 3. Example 3, what was about? Example 3. What was example 3? Ah, this one. Example 3 is this one. Then the question is, explain what exactly example 3 wants. Yeah, we want to prove this limit is infinite. Yes. And I wrote what it means. I don't understand your question. What do you mean? Exactly what example 3 wants. The definition, limit x tends to p f of x is infinity plus infinity, is by definition for arbitrary epsilon greater than 0, there exists delta greater than 0 such that for all x 0 less x minus p less than delta, we have f of x greater than 1 over epsilon. So f of x is sufficiently large. That's it by definition. And we checked by definition this. So what was question about? I don't understand. And I checked this precisely. Could you ask more precisely what you want? Okay. So I'll continue to reformulate results for the limits, what they mean for continuous functions. Of course, you should be careful because look, so for example, here you should suppose that P is a limit point, but in converse assertion, this need not to be supposed. Yeah. Okay. And then, so a couple of inequalities. For inequalities, a couple of theorems. For inequalities, then there was a theorem about arithmetic operations with limits, and it can be reformulated. So if fg from D to R, P in D, fg are continuous at P, then first f plus minus g are continuous at P. Second, f times g is continuous at P. Third, for g of P not equals to 0, f over g is continuous at P. So once again, we should consider no explanation. No explanation of the question from Masoud Wahid. Could you write an explanation for your question? Because for a while I don't understand what you are asking. Okay. So example 3 is here, if I remember correctly. So return to theorem 4. F plus minus g are continuous at P, f times g is continuous at P, and so on, right? So again, there are two cases. So first, P is not a limit point. Of G. Then we don't need to prove anything, because now the only thing which we ask for is just that the function should be defined at P, and that is true for all of them. Second, P is a limit point of G. Then continuity is equivalent to the corresponding limit. And then all of those assertions were proved for the limits. And that's all what we need. Okay, so that is about continuity. And maybe a nice corollary about discontinuity points of so classification of discontinuity points. So P, suppose F is defined at a neighborhood of P, but F is not continuous at P. Then P is a discontinuity point of P. First, P is removable if there exists finite limit as x tends to P f of x. It is not equal to f of P, of course, otherwise f would be continuous at P, but it is not equal. Why it is removable? Because you can define the function f by a different value, namely just by this limit, and after this redefining, the function will be continuous. Okay? Second, P is a discontinuity point of the first kind if there exists finite limits limit x tends to P minus f of x and f x tends to P plus f of x, but of course they should be not equal to each other. Why? Because if they are equal to each other, then there exists finite limit, hence P would be removable, but this is a different story. And third, all other cases P is a discontinuity point of the second kind. And what can be deduced from the theorem about limits of monotone functions? So theorem, okay, let it be theorem 5. If f is increasing on interval AB, then the set of discontinuity points is at most countable. And all discontinuity points are of the first kind. Proof. So first, in fact, here the second part of the assertion is immediate, because we know by the theorem about monotone function from the former section that one-sided limits exist for arbitrary increasing function at any point. Hence, any discontinuity point should be of the first kind for sure. But what is more interesting is that the set of discontinuity points is at most countable. Why? Because if P1 less than P2 are discontinuity points, of f, then limit as x tends to P1 minus f of x is strictly less than limit as x tends to P1 plus f of x, less or equal than the limit as x tends to P2 minus f of x, strictly less than the limit as x tends to P2 plus f of x. It follows from monotonicity. So we can choose there exists R1 in rational intersected with this interval, and R2 in Q intersected with second interval. And these are different rational numbers. So it means that for every discontinuity point, we can put into a correspondence a rational number. So there exists an one-to-one correspondence between the set of discontinuity points of all discontinuity points of f and a subset of Q. Hence, this set of discontinuity points is at most countable. It cannot be uncountable set. Okay, so that's all for today.